Let M be a 3 by 3 real symmetric matrix with eigenvalues 0, 2, and A with the respective eigenvector u, v, and w. Consider the following statement. First statement is a plus b minus equal to 10. The eigenvector x satisfy mx equal to v plus w. Statement 3 is if D is in span of UVW, then equation mx equal to D or system has a solution. The trace of m square plus 2m is 8. Which of the above statements are true? Options associated these statements or true statements given to us, and we have to find right one option. We will check these statement one by one. If we find some statement true or false, and on the basis of that we can discard options, but I will discuss each statement or validity of each statement to grab the concept of this problem. First, it is given to us 0, 2, and A are eigenvalues of real symmetric matrix. What is given to us and what we need to find? It is given 0, 2, and A are eigen values of M. Also, U, V, and W are respective or corresponding eigen vectors of M. A, B, C are either eigenvalues or eigenvector constituent. Now you can check here. These are eigenvalues, and U, V, and W are eigenvectors. In option A, B, C, A is coming from here, and B and C is coming the constituent of U. So to check the statement, first we need to find A, B, and C. So A, B, C are either values or eigenvector, whatever. It means A, B, C are somehow related to each other. It means eigenvalue and eigenvector have some common relation. And this is real symmetric matrix. This is real symmetric matrix. And in real symmetric matrix, a theorem we studied, eigenvector corresponding to distinct eigenvalues are orthogonal. Eigenvector corresponding to distinct eigenvalues are orthogonal. 0, 2, and A are eigenvalues. So first consider this pair one by one, 0 and 2, 0 and A, and 2 and A, and we will find relation between orthogonality of their corresponding eigenvectors. So I'm going to use first pair as 0, 2 are eigenvalues, are real distinct eigenvalues of M. So their corresponding vector or eigenvector will be orthogonal, and their corresponding eigenvector are 4bc dot product or inner product, you can say 111 is equal to 000. This implies 4 plus b plus c equal to 0, and this implies b plus c equal to minus 4. So call this equation 1. Their corresponding eigenvector are this or not. First I verify. 0 and 2. I am taking 0 and 2. So 4bc minus 1 to 0. 4bc minus 1 to 0. It is minus 1. It is minus 1, 2 and 0. So this equation will be minus 4 plus 2 times b equal to 0. This implies b equal to 2. This implies b equal to 2. Now we will check another pair as if 0 and a are real and distinct eigenvalues, then their corresponding vector will be orthogonal. So 4bc dot product with 111 is equal to 000 vector. This implies b plus c equal to minus 4. This implies from the above equation c equal to minus 6. We will obtain two eigenvalues b and c. Sorry, values of b and c, but these are not eigenvalues. Now I am going to check another pair. If 2 and a, because a is unknown, so value of a may be 2 or may not be 2. If we consider these are different or distinct, then their corresponding eigenvector will be orthogonal, otherwise not. If distinct, then minus 1 to 0 and a vector corresponding to eigenvalue a is 111 is equal to 0. This implies minus 1 plus 2 plus 0, which is not equal to 0. So 2 and a are not distinct. It means they are equal. This implies a equal to 2. Now at this point we have the value of a, b and c. A is 2, b is 2 and c is minus 6. By statement first, a plus b minus c equal to 10. So check this point. a plus b minus c is equal to 10 or not. We will check this point. Value of A is 2, B is again 2, and C is minus 6. So minus coming from this relation, so will turns to positive, is equal to 10. So statement first is true. Statement first is true. Now check another statement. Statement 2. Statement second. And what is this statement? This statement is saying that the eigenvector this satisfies mx equal to v plus w. This is v and this is w. So find their sum as a vector sum, and check that mx equal to this vector sum or not. First find v plus w, and v plus w will be minus 1 2 0 plus 1 1 1 is equal to 0 3 1. And what is x? What is x is given to us 0 3 by 2 comma 1 by 2. Because of 3 by 2 and 1 by 2, it will comes when we take half as a constant. It will be 0 3 by 2 and 1 by 2. So this vector can be written as this. So mx and x is 0 3 by 2 and half. X is this. So mx equal to, if I consider half as a lambda, so this is a mx equal to lambda x type of eigenvalues, or condition how to check eigenvalues. So we can write mx equal to u plus v plus w, mx equal to v plus w. This condition is true, or statement true statement. So statement second is true. Now I'm going to check statement 3. And what is this statement? Statement 3 is saying for any d which is in a span of u v w, the system mx equal to d has a solution for any. Remember this point, whatever the d, mx equal to d has a solution when d is in span, or span is linear combination. It means any d which is span of u v w, the system mx equal to d has a solution. Means every time we will find a solution, either maybe unique or infinitely many. It is not our concern, but we have a solution when d is in span of UVW. As 2, 2 repeated eigenvalue, or algebraic multiplicity of 2 is 2, our eigenvalues are non-zero eigenvalues. And how to check a system has a solution? By rank. These are non-zero eigenvalues. So number of non-zero eigenvalue is considered as rank of a matrix. So rank of matrix M is equal to 2, and which is less than 3, because of M is 3 by 3 matrix. M is 3 by 3 matrix. So it will has infinitely many solution has infinitely many solution and may not have any solution. It has infinitely many solution or may not have solution. Both conditions are true if rank of m and d is equal to rank of m, then have solution, and in this case infinitely many solution will exist because of rank is 2 not equal to number of variables. So one variable will be free and we can find many solution. And if rank of m or augmented matrix is not equal to coefficient matrix, then no solution will exist. So I'm going to test these two cases, and in these cases solution is existing or not. Now mx equal to d. So case 1, if d equal to 0 vector, if d equal to 0 vector, then mx equal to d has infinitely many solution because rank will be same, because of augmented matrix is same as coefficient matrix, and we know that the rank of coefficient matrix is 2, which is less than number of variable. So infinitely many solution exist. So this case is true. Now going to check case 2, when d is not equal to 0, d is not equal to 0 and d is in span of UVW. Span of UVW, it means d is in linear combination of UVW, and if d is linear or spanning set of UVW, then d can be written as or constituent of d if d is d1, d2, d3. These are constituent of d because matrix M is 3 by 3, so 3 constituent will be there. So d or di can be written as x1 a1 1, or this is d1 plus x2 a12 plus x3 a13, and similarly for other, and this system has rank same as rank of augmented matrix. Rank of MD is same as rank of M because D is in this solution. So D can be written as always in this type. Always in this type. That means D, or you will not get a row of 0 0 0 and non-zero value or non-zero value. So you will not get this type of any row in either augmented matrix or coefficient matrix, or in augmented matrix. So in this case system has a solution, but when this is not in a spanning set, then we cannot write d as a linear combination in this, and we will obtain a rank of this type 0 0 0 or non-zero type, and in this case rank of augmented matrix will not be same as rank of coefficient matrix. So this case is partially true. It means statement is partially true. Statement 3 is partially true or false. So this is wrong statement. Now check statement 4. The trace of the matrix m square plus 2m is 8. It means we know the all eigenvalues 0, 2 and a. These are eigenvalues. So we can find eigenvalues of m square and 2m. And sum of eigenvalues is considered as a trace. So we can check this trace is coming is equal to 8 or not. So 0, 2, 2 are eigenvalues of m, and we need to find trace of m square plus 2m. It means we will find eigenvalues of m square and 2m and add them. These eigenvalues will give you trace. So eigenvalues of 2m will be 0, 4, 4, and eigenvalues of m square will be 0, 4, 4. Now to find eigenvalues of m square plus 2m, so add these eigenvalues. 0, 8, 8 are eigenvalues of m square plus 2m. So their trace will be 0 plus 8 is equal to 16, which is not equal to 8. So this statement is false. So statement 4 is false. Now my true statements are first, second is also true, when, and third statement is false, and also fourth statement is false. So which one options is giving the information about true statement 1 and 2? That will be our right choice. Statement 1 and 2 is only true. Option B is giving the information about the true statement. So option B is our right choice.